electronic studies were made on two effects: the electromagnetic pulses and disturbance of the ionosphere as a result of nuclear detonations. To record the waveform of the electromagnetic pulse, two stations, positioned 100 miles and 460 miles respectively from the burst point, made broadband measurements from 0 to 10 megacycles. Signals received by vertical probe antennae were fed into oscilloscopes, and the resulting waveform was photographed. These studies were made on 7 different shots, including the Yucca balloon detonation. From a comparison of this information with actual shot data, it is hoped that the electromagnetic pulse can be used to approximate total yield when the time and location of the nuclear detonation is known. To study the disturbance of the ionosphere as a result of surface detonations, a C4-type vertical ionospheric sounder was installed at Kusai Island, 460 miles south of Eniwetok Atoll. Similar equipment was located at Wake Island. These sounders emit 50 millisecond pulses at 60 pulses per second, with frequencies from 1 to 25 megacycles. After the signals are reflected from the ionosphere, the received signals are displayed on oscilloscopes as traces. These traces were then photographed for later analysis. The results of this experiment agreed with similar studies made on Operation Red Wing. The energy responsible for the first ionospheric disturbance travels at about 12.5 miles per minute. The energy responsible for a second disturbance travels at about 8 miles per minute. In addition to the basic effects program, other experimentation was conducted on material reactions to nuclear detonations. These studies were concerned with aircraft structural tests, underground structures, electronic fuse components, thermal studies of skin simulants and uniform materials, and material ablation. In the aircraft structural effects program, the delivery capabilities of 3 aircraft types were examined. The B-52 first tested on Operation Red Wing, and 2 Navy carrier planes, the A-4D and FJ-4, both of whose responses to inputs from low-yield nuclear bursts were measured during Operation Plum Bob. The objectives of this program were to measure the structural responses of these aircraft when subjected to the effects of high-yield nuclear detonations. The particular response data sought on the B-52 were side loads imposed by the effects from nuclear explosions in order to determine the aircraft's capability for multiple delivery strikes, where blast and thermal loads could be received at any angle from weapons delivered by other aircraft. Overpressure input measurements for the B-52 proved to be approximately 10% less than predicted. The hardtack test results indicated that the analytical value for bending moment at wing station 1178 was a reliable guide to the capability of the wing. Fin and stabilization load data indicated that pre-hardtack correlation factors were appreciably below measured values obtained at some orientations. A more extensive analysis is now being performed to define the effects of overpressure diffraction loading and orientation on the fin and stabilizer responses. There was no evidence of damage from thermal energy or blast effects as a result of participations in the side-loading program. To aid in structural analysis of the A-4D and FJ-4, a method was employed for measuring transient input conditions on the wing as it was engulfed by the shock wave. This procedure utilized data obtained from several series of chordwise pressure pickups. Correlation data were obtained to examine the diffractional pulse and confirm the structural analysis by progressing from the shock waves measured overpressure input to measured aerodynamic reaction resulting from this overpressure, and hence to measured dynamic response of the structure. Using a conservative factor of 10%, the calculated input overpressures gave good correlation with the measured results. Satisfactory wing chordwise pressure distribution data were obtained. The data are sufficient that, from a careful analysis, the separate effects of overpressure propagation and gust velocity approaching from the trailing edge can be obtained. Although thermal input predictions were conservative, thermal responses correlated well. One participation, shot Walnut, resulted in minor thermal damage on the two FJ-4 aircraft which participated, with blistering on the underside, burning of seals between movable and fixed control surfaces, as well as blistering on the rubber surface on back of the central pod and on the rubber seals on the bottom of the fuselage. The underground structure study was made in conjunction with the ground motion studies previously shown. This program was carried out on hardtack in order to provide input data for designers of hard protective structures. Previous studies have been confined to low yields and Nevada soils. These structures, prefabricated corrugated steel flexible arch structures, were the targets for design studies on underground structural response to air blast and ground shock, the next step beyond the Priscilla findings of Operation Plumbob. Positioned in non-drag sensitive earthwork configurations of coral sand, they actually simulated balanced cut and fill buried structures. Inside the structures, floor slab accelerations, arch deflections, and internal pressures were measured. 3 of the arch shells were tested in the 80 to 180 psi peak overpressure region from COA's 1.4 megaton surface detonation, a long-duration loading test. Another was placed in the 90 psi peak overpressure region from the Cactus 17 kiloton burst to permit correlation of the effects of short-duration blast loading in a similar configuration. The Cactus tested structure, shown here, a 25-foot span by 48 feet, arch structure of 10-gauge metal, partially collapsed on the side away from ground zero. The collapse was apparently initiated by bearing failure of the shell plates at a bolted horizontal seam, about 5 feet above floor level on the collapsed side. A similar structure, subjected to 78 psi from shot COA, suffered a complete collapse symmetrically about the crown. The same effect was observed on a nearby 38-foot span by 40 feet arch structure of 1-gauge metal under 100 psi peak overpressure from COA. At 180 psi, another 25-foot span 10-gauge structure collapsed until the crown touched the floor. High radiation levels on the COA exposed structures delayed complete recovery operations for a number of months. Pending full analysis, it appears that the Plumbob design recommendations for this type structure are still valid. To establish design criteria for ICBM and other massive reinforced concrete structures under blast loads, thick reinforced concrete slabs were placed in COA shot's high-pressure regions, 175 to 600 psi, for dynamic behavior study. For this test, 30 slabs with reinforcing in one direction and 15 slabs with reinforcing in 2 directions were cast with spans of 6 feet and varying depths up to 5 feet. The slabs were placed flush with the ground surface to study flexure and shear strength, both with and without shear reinforcement. The results indicate that the resistance of the slabs to high blast pressures, particularly in respect to diagonal tension, was much greater than expected. After the high radiation level died down, the slabs were removed and examined to determine the magnitude and character of the permanent deformations. The data is currently being reduced and analyzed. One vital project expanded the Plumbob study of the effects of nuclear radiation on electronic fuse components and materials. The tests were conducted under simulated tactical and storage conditions, in which instrumented corporal missile fuses and allied components were buried in proximity to several bursts of kiloton strength. Magnetic tapes recorded the data for later recovery and reading. Fuses and numerous types of components were subjected to neutron exposures of from 10 to the 12th to 10 to the 14th neutrons per square centimeter, and gamma dosages of from 10,000 to 100,000 roentgens.